we go over the Haber cycle. Well, the Haber cycle is simply a special case of Hess's law. Now, Hess's law tells us that the enthalpy of something is the same regardless of all the stages that it takes. And so this is one special case of the Hess's law that we can be able to look at. The Haber cycle. Now, we've been given the first example here. Construct a Haber cycle and calculate the enthalpy of formation of magnesium fluoride from the data below. So we've been given all that data. Now the first thing we need to get to understand is what happens when you want to construct a Haber cycle. Well, for you to form magnesium fluoride, now what we are forming, as you can see, we want to form one more. So we need to deal with atoms so that what we are going to form is only one more of the magnesium fluoride. Now if we have got magnesium is a solid. It reacts with fluorine gas. This is going to form, let's put it here, magnesium fluoride, which is a solid. Now the energy required for you to form magnesium fluoride from magnesium metal and magnesium gas is called the enthalpy of formation. Actually, this energy, the enthalpy of formation, when you are forming a compound from the two atoms, the energy even lowers as the energy is lower than the energy of the individual atoms. So some energy is actually released in the process, because nature always wants to have minimum energy. That is the reason as to why chemical reactions happen. And now, this is not a direct process, as we can see. According to Hess's law, regardless of the stages, enthalpy is supposed to be the same. Well, we can see enthalpy of formation here. It would not be as direct as we can see here, because the stages are many. Now, before this happens, first the magnesium, which is a solid, has to be converted into magnesium in the gaseous form. And so we're going to have magnesium as a gas. And then we still have fluorine gas. Now this energy which is required to convert magnesium, which is a solid, into magnesium, which is a gas, is called the heat of sublimation or enthalpy of sublimation. Sometimes it's also referred to as the enthalpy of atomization, the enthalpy or the heat required to form an atom. So whatsoever name it can be given regarding what you've been given. So for this one, we've been given sublimation, and so we're going to use sublimation. If we are given the enthalpy of atomization, we use that one. It's the same. And so at this stage, for us to convert magnesium solid to magnesium gas, we need the enthalpy. If we say enthalpy is the same as heat of sublimation, well, if this happens, the magnesium, which is a gas now, can lose an electron, and such energy required for a gaseous atom to lose an electron is called ionization energy. And so first magnesium is going to lose one electron, and that will be the first ionization energy. And so we're going to have magnesium, which is a gas. Since it has lost an electron, it becomes positively charged. And then we have got fluorine gas. Where that electron it has lost, we can put it there. So there the energy involved is called the first ionization energy. The energy required to remove the first valence electron from a gaseous atom. After this happens, for magnesium to be stable, it has to lose 2 electrons. So this magnesium ion is now going to lose another electron. If it loses another electron, it becomes magnesium in gaseous form, and then 2 plus. Okay. And plus fluorine. Fluorine, nothing is changing. And so now the electrons lost become 2. The energy required to lose the second valence electron from a gaseous atom or ion is called second ionization energy. That is second ionization energy. Now after this happens, what you are going to see is fluorine can't react in the state in which it is as a gas, like that. So the bond between fluorine, the bond we can see like this, is supposed to be broken. Okay, supposed to be broken. And so we are going to break that bond for the reaction to happen. So we continue going. So we have got now magnesium 2 plus, and then we have got, so if we break the bond between two fluorine, a fluorine molecule, then we are going to have two fluorine atoms in their gaseous state, and then we have got 2 electrons. So such energy which is required to break a bond is the bond energy. Okay, so that is going to be the bond energy at that point. So we can put heat and then I can put bond there. That is representing bond energy. At times we might not see bond energy, but we are going to see atomization. So we can also call it as the enthalpy of atomization of fluorine. So I can put A there to represent atomization. That is for fluorine. Now when this has happened, well, this fluorine we can see here, there are 2 fluorine atoms, and each fluorine atom can take up 1 electron, and that is going to form fluorine ion, like that. And so because we have got 2 fluorine atoms and then we've got 2 electrons, what is going to happen is these electrons are going to be taken up by the 2 fluorines. And so what we are going to have, the energy is going to drop at this point. And so we are going to have magnesium 2 plus. Well, this is still in gaseous form. I didn't include the state symbol, which is a gas. And then when the 2 fluorine atoms takes in those 2 electrons, we are going to have 2 fluoride ions, like that. So these are still in gaseous state. Now when a gaseous atom gains electrons, such energy change involved is called the electron affinity. So electron affinity is the energy change when a gaseous atom takes in electrons, okay, or a gaseous atom gains some electrons. So at this point we have got electron affinity. Let me just call it EA. Now if we have got this in gaseous state, this in gaseous state, they can now react directly. So when these 2 react at this point now, this is what is now going to produce the magnesium fluoride. And so the energy involved here is called lattice energy. We define lattice energy as a heat change when gaseous ions react to form an ionic compound, and that should be one more of an ionic compound. So it can also be defined, the same lattice energy can also be defined as the energy released when an ionic compound, that is one more of an ionic compound, dissociates into its ions. So such is also referred to as lattice energy. So lattice energy can either be pointing down like that, or it can point in that direction. It is all the same. The only difference is when it is pointing like that, that means we have broken such a compound, okay, and then when it is pointing down, we are forming a compound. All right, now we can simply replace the values which we have here. By the way, another thing about lattice energy is it can either be positive or negative depending on what we have. So when compounds are reacting, when ions are reacting to form a compound, they lower the energy. Some energy is lost, and because some energy is lost, the value is going to be negative as you go from this point going down. But if you see lattice energy is positive, that means it is a compound which has been broken into its ions, because for you to break a compound you need to add energy to it. So that is the only difference that we need to get to understand. Now here we want to calculate the enthalpy of sublimation. All these other values we've been given, but the enthalpy of sublimation we haven't been given. Okay, so now what are we going to do here? Well, we can see that if we consider enthalpy of sublimation, the arrow is going in this direction. But for the rest, the arrow is going up here, the arrow is going up there, the arrow is going up, even here the arrow is going up, the arrow is going up, even here the arrow is going like that. In other words, everything, the arrow is going in the clockwise direction. But for enthalpy of formation, the arrow is going like that. So what is going in this direction should be equal to what is going in this direction. Okay. Alright, so now let's go on. So now this should tell us that the enthalpy of formation is equal to, so for us to find the enthalpy of formation, we are going to add all these other things. So we have got delta H of sublimation, the first stage, and then the next stage we have is first ionization energy, okay, plus first ionization energy, and then from the first ionization energy we add second ionization energy, okay, we have got second ionization energy. To the second ionization energy, you're supposed to add the enthalpy of atomization, and then plus, okay, now we can see here that it is 2 moles of fluorine which took in 2 electrons for us to form this compound, which is at this point. And so the electron affinity, we are going to multiply it by 2. Why? Because it is 2 moles here which are taking up electrons. It's not 1 mole. Alright, so that is 2 moles electron affinity. The reason is this: when you have got only fluorine taking an electron to produce fluorine ion, this is 1 mole. But if you put a 2 there taking 2 electrons, so that means the value of the electron affinity, you are supposed to multiply it by 2. Now let's go on and substitute the values. We see what we are going to find. So what we have here, let me write it there. The enthalpy of sublimation. Now what is undergoing sublimation is the magnesium. It's been given as positive 150. And then we have got first ionization energy at that point, which is 735. And then the second ionization energy, which is 1445. And then what else do we have? We have got now enthalpy of atomization. This is the atomization for fluorine. Okay, so the enthalpy of atomization for fluorine, which is also the bond energy. So depending with what you've been given, the energy required to break this bond between fluorine, atomization of fluorine, or the bond energy for fluorine, and the value is 159. And then we have got plus 2. Okay, there's also one thing that I've left. I've not added electron affinity, lattice energy. We're going to add it. We have got 2 electron affinity. The electron affinity has been given here, that is negative 328. So let's add what we left on the first stage. We are supposed to add also the lattice energy. Now the reason as to why we can see the lattice energy is negative is because it's going in this direction, and so we're going to add it direct. So that means if the value was positive, that would have shown that it's going like this. So we should have subtracted lattice energy instead of adding if it is going in the opposite direction. And so plus delta H lattice, just that I don't have much space there. So let's go on and add at this point. So we are saying plus the lattice energy is negative 2957. Okay, now if we add these, if we sum them up, that is supposed to give us negative 1124 kilojoules per mole. So it is kilojoules per mole because what we are forming is 1 mole of magnesium fluoride. Let's consider another question here. Construct a Born-Haber cycle and calculate the lattice energy of magnesium chloride. Well, again we have got magnesium chloride. It's really the same thing. It's just that here we want to calculate the lattice energy. And so the magnesium chloride is formed from magnesium, which is a solid, and then plus chlorine, which is a diatomic gas. So when these two react, that is going to form magnesium chloride, which is a solid. Well, the energy that is required for you to do that, to form magnesium chloride from magnesium and chlorine, is called the enthalpy of formation. Now at this point, this doesn't just happen automatically. First, this has to ionize. Now, as we can see, we've been given first ionization energy and second ionization energy. At times, we can just be able to combine these two, and we are going to say magnesium. So when the magnesium loses 2 electrons, instead of writing those two stages alone, we can just say magnesium 2 plus chlorine gas, and then plus 2 electrons. Well, this is not the next stage, but at times you can just go direct like this. Okay, if we just go direct, that means we are going to combine the first ionization energy and the second ionization energy, if we don't want to waste a lot of time. But better we just follow each stage as it goes. Now, before even losing an electron can't be lost in solid state. This first has to ionize into gaseous state. Okay, and so what is needed there is magnesium, which is now going to go to gas, and then plus chlorine, which is a gas. So the energy required for this to happen is called the enthalpy of atomization of magnesium, or the enthalpy of sublimation of magnesium. And after this happens, now the magnesium can be able to lose the first electron to become magnesium plus in gaseous state. Then you've got chlorine gas, and then you have got 1 electron lost. So the energy required for this to happen is called the electron affinity. Okay, and that is the first electron affinity, to lose the first valence electron. After this happens, then the magnesium plus can now also lose another electron, a second electron, to become magnesium 2 plus. And then we still have chlorine, which is a gas there. And so now they become 2 electrons lost. So the energy required for that to happen is called the second ionization energy. Now, when this happens, this chlorine is going to now atomize. Instead of it being a chlorine like this, we are going to break this bond, because we can't make this reaction start working before breaking the bond. So we are going to break that bond which is there. So to break that bond, the energy required is called the bond energy, or the enthalpy of atomization of chlorine. So we're going to have magnesium 2 plus in gaseous form, and then we are going to have now 2 chlorine atoms. They are now atoms in gaseous form, and then we have got 2 electrons. So the energy at this point is called enthalpy of atomization of chlorine. We shouldn't confuse this with this. Okay, now after this happens, after we've broken the bond, then each chlorine can now take up 1 electron, as we can see for chlorine. So when chlorine, which is a gas, gains an electron, this is going to form chlorine minus, and this is a stable form because chlorine lacks 1 electron in the outermost shell. And such energy required for that to happen is called electron affinity, the energy required for a gaseous atom or ion to gain an electron. And so now what we are going to have is 2 chlorine ions, because each chlorine atom has gained 1 electron. Now we can see that 2 moles of chlorine have gained an electron, so we are going to have 2 electron affinity, 2 times electron affinity. Now the energy involved direct from this point to the down is called, okay, the name is referred to as lattice energy. Now that depends on which direction we want to go. If the arrow points up, we need to know that the value of the lattice energy is supposed to be positive. Why? When you are breaking a compound, you have to supply energy to it. That is why the value is positive. But when you are forming a compound from ions, energy is lost. That is why the energy is negative. So the way I've put the arrow pointed up, we expect that the lattice energy is supposed to be positive. Well, is going to be positive, yes. Now from the reaction we have to change just something. We can see now that this and this, they are pointed in the same direction. As we can see, everything going in the anti-clockwise direction should be equal to everything going in the clockwise direction. So these, from this point, from this arrow which is here, we are going like this. All the arrows are pointing in that direction up to this point which is here. And then the enthalpy of formation and the lattice energy, the arrows are pointed in that direction. And so this value plus this value should be equal to this plus that plus that plus that and also plus that. Alright, so that is all the thing that we do. Well, if the arrow was pointed in this direction, that means the enthalpy of formation would have been alone. Okay, now let's go on and sum them up. So we are saying the enthalpy of formation plus the lattice energy should be equal to enthalpy of atomization of what? Of magnesium plus first ionization energy plus second ionization energy plus enthalpy of atomization of chlorine, and then plus 2 times the electron affinity. Now we go on and substitute the values. The enthalpy of formation, we've been given the value there, and so we have got negative 642, and then plus enthalpy or the lattice energy, and that should be equal to enthalpy of atomization of magnesium. It's there at that point, and so that is 148 plus, what else do we have? We have got first ionization energy, which is 738, second ionization energy, which is 1451, and then we have got enthalpy of atomization of chlorine. This is the chlorine molecule. Okay, enthalpy of atomization or dissociation of chlorine. It's really the same. Atomization, dissociation, or bond energy. All talks about the same. That is 242. And then you have got 2 times now electron affinity. Okay. The electron affinity, the value has been given there as negative 349. I don't know if that is visible. Let me write it somewhere here. Negative 349. Okay, like that. We can go on and just punch those values. We have got lattice energy there, and that should be equal to, so the first value we have is 148 plus 738, and then the next one is 1451, the next one is 242. Okay, so that is what we have. And then the next value that we have at this point, okay, we have got 2 times plus 2, which is times negative 348, and that is giving 1883. Now to remain with this value, we are going to take this the other side. So we are going to remain with lattice energy being equal to 1883 plus 642, and that's supposed to give us positive 2525 kilojoules per mole. Alright, so that is the value in this case, the lattice energy for this question which we have at this point. Alright, now let's go on and look at another question. Construct the bond Haber cycle and determine the bond energy of 1 mole of chlorine from the following data. Now for here, if we just look at the enthalpy of formation, we are talking of the formation of sodium chloride. And so we're going to have sodium chloride at this point. Okay, first we have got sodium atom, which is in solid state. It reacts with chlorine gas. Now what we want to form is sodium chloride, which is a solid. Well, when we can look at this compound, this is one more of compound. Now we need only one atom, one more of sodium, and one more of chlorine. Now we can see here we've got 2 of chlorine. And so what we need to do is we need to balance this reaction. Instead of putting a 2 in front here, if we put a 2 in front there, that means we're going to form 2 moles of this compound, but we don't want to form 2 moles. When you're talking of enthalpy, as we can see, we are talking of per mole. We are interested in 1 mole. And so to balance, we are going to instead put a half in front there. Alright. Now, the energy required for this to happen from this point, when this reacts, sodium, which is a solid, reacts with chlorine gas, that is the enthalpy of formation. Okay. Now this, before this happens, sodium first has to atomize, or it has to undergo sublimation, the process in which a solid is converted into a gas. And so we're going to have sodium in gaseous state, and then plus half chlorine molecule. And such energy is called enthalpy of sublimation or atomization. This is atomization of sodium. Well, after this happens, now the sodium can lose 1 electron, and that becomes sodium plus gas in gaseous state, and then you have got half chlorine in gaseous state also. We have lost 1 electron, so an electron comes here, and the energy here is ionization energy. So sodium, for sodium, we're only interested in first ionization energy, because only 1 electron is lost from the outermost shell to be stable. Actually, sodium only has 1 electron in the outermost shell. Alright, so it can lose other atoms, but those will not be from the outermost shell. We are going to be losing electrons from the inner shells. Now when this happens, this chlorine has to atomize, and so what we are having is this. We have got half chlorine molecule, that is ClCl. So when this bond breaks, we're supposed to have 2 Cl like that, but these 2 and this 2 is going to cancel, so we're just going to remain with 1 chlorine atom. Okay, because of the balancing that you've put there, the half. And so what we are going to have is sodium plus in gaseous form, and then plus chlorine in gaseous form. I use solid here, this is the gas, and then plus an electron. So the energy involved there to break this bond in chlorine to just chlorine is called bond energy, or enthalpy of dissociation. It can also be called as enthalpy of atomization of chlorine, depending with what you've been given. So after this happens, now the chlorine, which has already been broken, can now gain this 1 electron. Okay, well, we would have noticed that when we reach to the point of electron affinity, the arrow is dropping instead of, why aren't we just writing it up, going up? The reason is because all these values we are seeing at this point is they are taking in energy, but electron affinity energy is lost. That is why we can see the arrow starts to point down, because energy is lost. Alright, so what we are going to have is sodium plus, and then plus chlorine. Okay, we have got chlorine gas. Now it has taken in an electron, so it will become a chlorine ion like that. And then now let's look at the lattice energy. The lattice energy given is negative. That means the value you've been given is from there to there. If it was positive, that means it would have pointed in that direction. So that is the lattice energy. And so to find enthalpy of formation, we are going to add everything, this value, that one, this one, and this one, because they are all pointed in the same direction. And so what we are saying is enthalpy of formation is equal to enthalpy of atomization for sodium plus ionization energy plus enthalpy of atomization for chlorine. And then what else do we have? And then we have got plus electron affinity. Now enthalpy of formation, we've been given here formation, the value is there, that is negative 410.5. That should be equal to atomization for sodium, the value is there, that is positive 107.3. Ionization energy, the value is given, that is 495.8. And then you've got enthalpy of atomization for chlorine, which we don't know. Okay, so let me just put it there. Now one thing that we need to get to realize is for chlorine to atomize, we can see that it's a half mole which is atomizing. So we are getting half mole, that is what is being converted into chlorine atom. And so at this point it is very much important. I should have just put a half at this point here, because it's only half mole which is going into that, it's not 1 mole. Alright, so that is very important. Just like for the previous questions, we are multiplying this one by 2 because there was a 2 moles here, but for this one there's no need even to multiply by 2 because it's only 1 mole involved. So at this point we have got half enthalpy of atomization. We know that this is for chlorine, I can just write it like that, and then plus electron affinity. Electron affinity is there, it is negative 348.6. So I can go on and calculate, that is negative 310.5 being equal to 107.5, I mean 0.3, plus 495.8. And then okay, we add this and this, from there we go to this one which is negative 348.6. so what we have is positive 254.5 and then plus half enthalpy of atomization. Okay, and so what we are going to do is we are going to take this value the other side, and so that is going to give us 254.5 minus 410.5, that is going to be equal to half enthalpy of atomization. So 254.5 minus 410.5, that gives negative 156, that will be equal to half enthalpy of atomization. And so we are going to cross multiply, so that is going to multiply by that, and that is going to give atomization, enthalpy of atomization to be equal to negative 312 kilojoules per mole. So that will be the value for this question at this point, as we can see. Okay.